This is just an intro session to the Splunk Machine Learning Toolkit. Gives you an idea of what it is, how it works, and what you can get from it. So without further ado, we'll go on and look at the agenda. So things we're going to cover today. What do we mean by machine learning in terms of, it's one of those terms that gets bandied around quite a bit, and I just want to sort of bottom out before we even start talking about the Machine Learning Toolkit. What do we mean by machine learning? There's a little bit on terminology and concepts. Then what does the Machine Learning Toolkit do in terms of bridging the gap between what is, industry standard machine learning concepts and Splunk as a product? Then a very quick bit on how do you get it, how do you install it, how do you set it up, before we go on and have a look at using it in anger, so to speak. Then second half, I want to talk a little bit about some really important things that effectively, if you're not aware of them, they can really have adverse effects on how much value you can get out of the Machine Learning Toolkit. And that's to do with the importance really of understanding about shaping and scaling your data to get the most value out of the various algorithms and how they function as well. And so off the back of that, we then look at avoiding common pitfalls, because ultimately we want people to get the most value out of this. So here are the things not to do really. And then finish off really with a bit of useful resources. So some of this I'd sort of say is Splunk specific, so reference actually the MLTK. But more generally, I think people will get the most value out of the Machine Learning Toolkit if they understand machine learning as a concept and understand all the various elements that surround that. So what do we mean by machine learning? So you've got that very, very wordy definition from Wikipedia at the top there. Whilst yes, it's absolutely correct, I think if you were to show that to many people, it would sort of make their eyes glaze over a little. What I want to do here today is to sort of simplify what do we actually need to know if we were going to talk about machine learning, and specifically the little bit at the bottom, keeping it simple with bullet points. Machine learning effectively is a branch of mathematics almost, where you use various different algorithms and statistical analysis methods in order to produce your outcome. And specifically on that second point there, the difference between sort of using stats in a simple, straightforward manner and versus machine learning is, traditionally, if you wanted a computer to do something or a program to produce an output for you, you had to know what the output you wanted was, and then you had to go away and you had to program specific sets of instructions for that system to produce the output you desired. The thing with machine learning which differentiates it from that is effectively we have an algorithm, we have a data set, and we let the algorithm free on that data set, and effectively it will produce an understanding, which is the machine learning model, without having ever been told how to produce that model or how to sort of code the sort of settings of that model. And as I said in point 3, yes, it builds that mathematical model for us. There are many applications and use cases of machine learning, and when we go on to the actual sort of hands-on stuff in a short period, I've got a few examples from the showcase in Machine Learning Toolkit, and you can see how your data from multiple different sectors of industry can be used in many different ways in order to produce some useful insight. And then finally, just before we go on to sort of terminology and the various aspects there, is sort of hammering home this difference between AI, machine learning, and deep learning, and I'll come on to that in a second. So just to sort of make this clear, and it's one of those things I come across quite a lot when dealing with people and with customers, that certainly the first two terms, AI and machine learning, tend to get used interchangeably, and they are distinctly different things when we are talking about this from a technical perspective. So as it says on the slide there, AI is literally anything that can simulate human intelligence by any means. Now, this can be a system that predicts whether someone is a child or an adult based simply on their weight. So if you say, if the weight is less than 50 kilograms, child, if it's more than 50 kilograms, adult. That's AI in a nutshell. Machine learning is sort of the same thing. except it gets a lot more complicated, and it can take multiple inputs, and it has sort of far more complicated algorithms behind it in order to produce the end result. But effectively, it's kind of the same thing. Now, deep learning is something that isn't yet, or it is, but it isn't. At the moment, the MLTK doesn't quite do deep learning. There is, and it's not mentioned in this webinar, there is the option to connect Machine Learning Toolkit to a sort of TensorFlow instance, but that's something that's currently sort of in beta, so we won't really go into detail about that today. But deep learning is kind of the same thing, but it has multiple layers. And if you imagine the way that the neurons of a human brain connect, similarly, you will have little nodes within a neural network for deep learning, and it does the same thing. The word deep effectively comes from the fact that you have separation almost between input and output by multiple different layers in that neural network. But yeah, just to clarify, the differences between the three main terms there, and also point out that, to say, deep learning is not yet in the product. Other terminology that's important to understand as well is, and again, this is before we get into MLTK, it's machine learning territory purely, this one, is things like the difference between supervised and unsupervised learning. Now, supervised is where we say something like, I'm going to show this algorithm 100 examples of fraudulent activity and 100 examples of non-fraudulent activity, and I'm going to let the model, the algorithm, know as it's building and testing itself which ones are fraud and which ones are not fraud. So that's like labeled data, and we call that process supervised learning, because as the algorithm is going through its various iterations and trying to refine itself, it knows at each point whether it is right or wrong, and therefore can adjust itself continuously, and the idea being that it gets closer and closer to being right more and more of the time. Unsupervised learning, by contrast, is where we have a whole bunch of data, there's no labels on it, and we just want to know what interesting insights are in that data, what patterns are in that data, for example. And so on the slide there, you see we use k-means clustering. So an example of something like k-means clustering that you might want to do, classic one would be something like Tesco Club Card. So every time you go into Tesco, you buy products X, Y, and Z, you get to the counter and you scan your club card, and now you've told Tesco, I am this person, and here are the products I buy. Now, that happens for each and every customer going through, and very quickly, Tesco build up this huge repository of data about persons and purchases. And what they can do is then start to say, well, where are the patterns, where are the clusters in that data? So that, for example, if 100 people buy a certain brand of tea bags, and the 90% of that sort of group of people also buy another product, but the last 10% don't, well, you bet yourself that the next vouchers that you get through the post, if you're in that 10%, are going to be for the product that every other one in that cluster buys, but you don't. So it's about being able to identify those patterns in the data in order to be able to say, actually, here's an opportunity we were not exploiting, really. The other one that I've used k-means clustering with is if you take, for example, a military context here. If you have radar data on where potentially enemy aircraft may be coming from, and you only have limited resources in terms of anti-air defense weapons, you really want to be pre-positioning those weapons in the best place possible to minimize the time for response if you ever happen to come under attack. And so you can use, again, k-means clustering, and then once you've got your clusters identified, you can then say, well, okay, within these clusters, what's the median altitude or the median intercept heading, and really focus in your assets exactly where they're going to do the most for your defense. So that's supervised and unsupervised learning. Data munging. Now, this is something that is hugely important when it comes to machine learning. In the past, when you talk about big data and these sorts of things, it's sort of always been the case that just throw as much data in as you can. It doesn't matter what data it is, just throw it all in. The more data you've got, the better things will work. And in fact, Microsoft put out a paper, I think it was, called the unreasonable effectiveness of data, showing that actually improving an algorithm necessarily wasn't the way to get better results. It was just to throw more data at it. It's not quite really the case if you want to get the best value out of machine learning. And we'll come on to a specific example a bit later, but effectively data munging is look at the data you've got, look at the format it's in. Is it in a format that makes sense? Are there sort of features in your data that aren't explicitly stated, but perhaps you could extrapolate them from other features? Are you sort of recording data features that actually aren't really particularly relevant to the question you're trying to answer? So you really want to be sort of extrapolating as many relevant factors from your data as possible, but also looking to remove irrelevant or potentially irrelevant factors. And also, if you can take two factors in your data, two elements, and say, well, actually, these are different elements, but they effectively tell me the same thing. So do I need both? Because the fewer elements going in, the fewer things that sort of muddy the waters, the more likely it is that you're going to be able to produce a useful outcome using machine learning. And then finally on this slide, there's not one size fits all algorithm. And this is something that, at Somerford, we're quite keen that we don't go in the way that many people have, which is, all in for machine learning. Machine learning is this magic fairy dust that you can sprinkle onto anything and make it better. Absolutely not. No, you want to understand it properly. You want to know that actually there are specific algorithms that are very good at one thing, but really not very good at another thing. And so when we talk about machine learning, we have to say, well, actually, it's something we need to be very specific about which algorithm we use, which method we use, how we format the input data, and so on. And so you see here we've got prediction, forecasting, clustering, and outlier detection are common groups of algorithms, and within each of those you'll have many different ones. One thing to be sort of aware of again, and it's one of those things that in common language might often be confused. So if we say the weather forecast or the weather prediction, we effectively mean the same thing. In machine learning, prediction and forecasting are two distinct things altogether. So prediction would be if the temperature is 30 degrees outside, how much ice cream will I sell? So there's no time element there. Forecasting is if I've sold this much ice cream in June, how much ice cream will I sell in July? So there's a time element there. So if you're looking forward to predict a variable based on time, then you're forecasting. If you're just looking to predict a variable based on another variable, then you're predicting. So where does MLTK come in, and what is it for? As a top bullet point there states, it really is about lowering the bar of entry to machine learning. So the picture on the right, if you can see it, is quite a simple example of using Python for an implementation of TensorFlow. But to most people, they'll look at that and go, oh, I don't know what that is, and I don't like it. It looks complicated, even though in terms of doing machine learning in Python, it's relatively simple. What Machine Learning Toolkit does is it takes what you see on the right there and it turns it into very, very simple SPL. So if you've basically used Splunk for any period of time at all, you'll be familiar with the Splunk search query language. And what Machine Learning Toolkit does, effectively, Splunk made the decision not to try and make their own implementation of machine learning. Rather, they went out and said, well, what are the industry standard tools that are out there? So you have scikit-learn, you have NumPy, you have pandas, and all these libraries are out there already that are, they are industry standard. And they said, you know what we'll do is we will incorporate those industry standard methods and those libraries. But what we'll do is, because it's very complicated and people don't like to learn a new programming language in order to do that, they're familiar with Splunk as a product, what we'll do is we will put Splunk as a front end in between the industry standard tools and the user. So anyone who's familiar with the Splunk search language can begin really quickly being able to do machine learning. And so, yeah, second bullet point, I'm sort of going off on little tangents here, but second bullet point, Splunk itself, when I was talking earlier about data munging, you'll know about being able to, like, for example, do lookups in Splunk, being able to do value statements to bring out a new field or any of those sorts of things. So you can actually do that filtering and munging of your data to make it fit most effectively with machine learning element in Splunk. And yes, that's the other bullet points there. I'm not going to go into any great detail, but yeah, it allows you straight away to work machine learning with data you already have. And as we all know, Splunk is all about visualizing your data. So how do you get it? Really simply, it's a free app, nothing to pay for or anything like that. There's two elements to it. So although the Splunk Machining Toolkit is the front end that the user will use, as I mentioned before, you've got all those industry standard libraries. They come in the Python for Scientific Computing app. It's a separate app. It is a prerequisite. If you forget to install it, it's not the end of the world, because the first thing the Machine Learning Toolkit will say to you is, you haven't installed Python for Scientific Computing. Please go and do so. But the main thing here is, as you can see on that sort of sub-bullet there, it's important that you get the right version for your operating system. There are 3 versions. There's the Linux, the Windows, and the Mac version. In production, most customers of mine have always been Linux, but there are some out there that will use Windows and so on. So just be aware and make sure you install the right version. You install it on the search head. And where I say here that you've got additional considerations in a cluster, typically, so what this applies to is when you train a model in the Machine Learning Toolkit, you can save that model. And if you save that model, it effectively gets saved out as though it were a lookup in Splunk. So within Machine Learning Toolkit app, you'll have a lookups folder, and the saved and trained models will go in there. Now, I apologize if I'm telling people things you already know here, but obviously when it comes to machine learning, training the model is the hard part. That's the one that requires the most compute. Actually applying the model is relatively simple. It doesn't take a lot of compute to apply a pre-trained model to your data. So when I say about search head clustering here, what I'm really saying is that it's typical, if you have search head clustering, that you would have a standalone search head which can still access your indexing tier, which is, additional resource applied to it. There may be tunings in the configuration files to, tweak upwards certain limits, so that it's able to really get in amongst your data and throw itself into that difficult compute task when it comes to training the model. And then what you'll do is you'll take that trained model, put it over, for example, to your search head deployer, and then deploy it out to all the members of the search head cluster so they can all do the easy part, and this standalone search head doesn't interfere with the running of things in your cluster. So how do we use MLTK? So again, I'm probably harping on a little bit about munging your data, but it really is important to understand. So what we have here, so this is the sort of landing page in the Machine Learning Toolkit. The great thing about it, and I think something really good that Splunk have done, is for each and every type of algorithm, they've got multiple examples here, and you can see here, for example, predict numeric fields. So we talked earlier about prediction and forecasting. So this is, if X is 5, what is Y? For example, those sorts of things. Categorical fields. So if you're looking for the classic example, you're looking through your data, your sales transactions, and you're looking for fraud versus not fraud. So that's, categorical things there. Numeric outliers. So again, if you are your sales, for example, we normally never sell more than X amount of a product in a given month. Why are we suddenly selling a huge bunch more? Have we perhaps, if you're Amazon, for example, and you're selling electrical goods, has someone accidentally put a 42-inch screen on at $9.99 and suddenly they're going out the door like nobody's business? So there's your numeric outliers use cases. Categorical outliers, again, this is very similar to numeric outliers in some respect. So the examples there being, for example, outliers in mortgage contracts. So, is someone likely to default on their mortgage, for example? Forecasting time series. So again, when we spoke earlier about forecast versus prediction, this is, I have historical data about the things I'm seeing. So internet traffic is one example there, monthly sales is another. So if I know how things have gone in the past, how might that allow me to predict forwards into the future? And a slight variation on that Splunk have recently introduced is this smart forecasting. So, for example, if we wanted to predict the sales in the US of fireworks and beer, then we probably shouldn't use the 4th of July as a reference point. So as you see here, it allows us to select certain special days and say, maybe don't look at this one with as much gravitas as you would any other given day. This one we know is an exception. And similarly, if you wanted to say, well, don't consider the weekends because we're closed on weekends. So that sort of thing. It's a slight improvement on the forecast time series. And then the clustering, this one here is the one I spoke to earlier about as well, like Tesco Club Card. But there's other things like predicting what vehicle the data came from based on the values of the data. So have a look at some of these. I'm just going to show you this one here. So this is a bit of server power consumption here. So it is predicting a numeric field, and it's a straightforward linear regression. So I'm not sure how familiar you are with the various different types of machine learning algorithms that are out there. I'll give you some resources at the end. But effectively, linear regression is one that we all learned in school, and it's the old y equals ax plus b. Really, probably one of the simplest of machine learning algorithms to understand. But effectively, what we have here, and this is in the showcase, so we've said that what we want is we'll bring in this data here. So this is just a straightforward input lookup. This could have been a base search. So you could have said, okay, index equals OS and source type is whatever, and get the same data. But all we're doing for the sake of simplicity is we're bringing in data through a lookup to a CSV, applying the very simple linear regression algorithm, and we want to predict this field here, the AC power. And what we are using to predict that are these 8 fields here. So we're saying we think that the power is probably a function of CPU utilization, disk access, and so on and so forth. Then something else which is really important if you want to understand the accuracy and reliability of your model is to split your data. So you have some training data and some test data. What we've done here, this is just the out-of-the-box setting, is we split the data. So all the data that comes from this CSV here, we split it down the middle and said, right, what we're going to do is we're going to train the algorithm on one half, and then what we're going to do is we're going to validate that the algorithm does what we think it does by testing it on data it's never seen before, and we'll see how close the predictions are to the actual values. And I can show you just how simple this is. This is obviously the showcase, but I can show you the SPL here, and you can see just how simple the actual search is. So we have, there's our base bit that brings our data in. And then what we're doing is we are using the fit search command. We want to identify what the value of the algorithm is going to use is linear regression. We want to fit is to predict this field, the AC power field, from these fields. And when you compare how simple that is to the Python TensorFlow example we had in the slides a few minutes ago, you'll see that machine learning toolkit really does make things a lot easier and much quicker to get into sort of your operational environments. So here are the results, and we've got the various fields there. We have the actual AC power, which is the first column, and then the predicted AC power, which is the second column there. And you can see that they are off a little bit in here and there, but on the whole, they're pretty good. And then we have down here sort of some visualizations of those same things. And down here, in the bottom left here, you've got your R-squared statistic, and then this one here, which is the root mean squared error. And again, I don't know how familiar everyone is with machine learning, but root mean squared error, it's an interesting thing to understand, and I'll probably just go back up here and just say, this one here on the right, the actual versus predicted scatter chart, is a good way of understanding how we calculate the reliability and the accuracy using the root mean squared error. So effectively, you've got this yellow line here, and that's, as we all learn in school, sort of a line of best fit. But some points are below the line, some points are above the line. How do we know that really is the best fit? And so we take what's known as the root mean squared error, which is if a value or a point lies below the line, we give it a negative value. If it lies above the line, we give it a positive value. Now, if we just did that and nothing else, and then we summed them all up, we could sometimes perhaps end in a situation where our calculated error is 0, and yet there are clearly points above and below the line. That's because the points below with the negative value might actually cancel out the points above with a positive value. So what we do is we square all of the values. So the negative ones become positive, the positive ones remain positive, and then we take the square root of that to give us the total variance from the line. Now, that gives us, like say, the root mean square error. So we take the square root of the mean, and we get this figure here, which is, in this case, 5.61, and you'll see this one here sort of marries up quite well. Effectively, 5.61 means we were about 94%, 94.5% accurate, roughly, with that. So that's a linear regression, looking at power. We'll look at a few others. And this one here, so this is like categorical fields. So, again, it's here we're identifying a vehicle, but this could be, fraud or not fraud. And we're using a slightly different algorithm this time, which is logistic regression, which is in many ways similar to linear regression, but slightly different. And we're looking to predict the vehicle from these fields here, which, as you might put in, you think, well, actually, yeah, the voltage, the voltage might vary from one vehicle to another. So actually, yeah, that is a relevant field to include. Same with the various other ones as well. So, and again, we've split on 50-50, and you can see here, first two columns, prediction. I'm just trying to see if he's got them right pretty much in all of them, actually. So there are many others, so numeric outliers, and as you can see with all of these, and this is something I'd strongly suggest if you go on to use machine learning toolkit, is don't necessarily think that you have to start from a blank canvas. For every kind of use case you've got, in the showcase, you have examples, and the only thing you really need to change is this first line here. That's your based search, that gets your search, and it gets your specific data in and ready to be used. And then, obviously, if you're predicting something different, then you would change things like this and this. You can play around with the algorithms. So you've got LLP, there's LLT, LLB as well, I think. All of this is actually quite well documented in Splunk docs as well. But you can really see from what they've done in the showcase how you can just basically transpose their work, steal it almost, and save yourself a lot of hard work and time figuring out where to go and what to do. So shaping and scaling your data. This is something I've mentioned munging many times, but it really is important. So that's why I focus on it so much here. So certain algorithms you will find will perform so much better if you do a little bit of work on this. And so the ones to mention here, so principal component analysis is if you look at the top right there, you can see there's various different data points, but there are two main features there. That there's the how far left or right along principal component one the point is located, and then how far up or down along the principal component two the data point is located. So effectively, if you imagine that we could have something on the order of 10-dimensional data here, so 10 different components that have to be represented, which would be very difficult for a human to visualize. But you might find that within that 10-dimensional data, there's a single direction or line that things sort of all, regardless of what dimension they're in, they all sort of seem to fit along it. And so instead of feeding your machine learning model or your algorithm with 10 different things to think about, you can reduce that down without really losing much of the essence of the meaning of the data into 2 or 3 principal components. So you're working on a far smaller data set without having actually lost much of the meaning or the value of that data. So looking at the bottom right, this one is again the same sort of idea. It's a dimensionality reduction. So you're taking 10 dimensions of data, or in this case, the bottom right, the picture on the left with the little curled color thing. We can look at that and go, oh, brilliant, that's a 3-dimensional thing. But actually, we can unroll it, and now we can represent the same data without any loss, but in 2 dimensions. So we're making the problem easier for ourselves and just simplifying things, therefore being more likely to be able to identify the patterns and get more accurate predictions or forecasts out of our machine learning model. And then finally, on the bottom left, we've got standardization. And I'll touch a little bit more on this in a sec, but standardization is about making sure that we don't confuse the algorithm when we pass data into it, because certain algorithms work really well when the values you give them vary between 0 and 1. And say, for example, we had I don't know, some data about someone being present or not present. So we can represent that with 0 and 1. So 0 is not present, 1 they're present. But we want to know what days of the week they're present on. So let's go Monday to Sunday, and we'll number those 1 to 7. Well, certain algorithms will look at the 0 and 1, and they'll say, okay, I understand the relative importance of that. Oh, but Sunday's got a 7, so it must be 7 times more important than the 1 in the present field. So in order to avoid confusing algorithms like that, what we do is we standard scale our data. And so we look at the standard deviation, and we then reshape each value as an amount of deviation from the standard. So therefore, we actually have everything as a value between 0 and 1 scaled relative to the max and min within that field. Avoiding common pitfalls, yes. So I talked earlier, quite a bit actually about data munging. So selecting the correct predictive fields for your target field. And when I say here the red tie example, imagine we want to train a machine learning model, and what we want to do is to predict how much it's going to cost for any given journey in the UK. So things that would be relevant to that are like, where's the starting point? Where's the finishing point? What's the distance between them? Are we going by car, by bus, by train, by plane? What day of the week and what time of day are we going? Because all these things have an influence over the cost of our travel. But if we go by the old way of thinking, well, just throw as much data in as possible, we might also put in, what am I wearing? Am I wearing a blue tie or a red tie? Well, if we put that data in, great. We've got more data when we want to look at our problem. But actually having values in fields there that the machine learning algorithm has to look at and has to understand and has to try and factor into its calculations, which are completely irrelevant to the actual required target field, it just reduces, almost invariably it will reduce the overall accuracy of what your model can produce for you. So when we talk about data munging earlier, it's precisely this sort of thing we want to avoid. We want to do not give the model things it doesn't need to know about. And then next we've got selecting less than optimal algorithms. So if I quickly switch back, I want to just show you what I mean here. Right, so I think, yeah, over here. So this is from an app called DGA app. And what the DGA app is looking to do is, if you imagine in the case of malware, quite often malware, when it gets onto a system, it tries to determine, is it on a normal live system, or is it in someone's lab being reverse engineered in order to provide a fix? And one of the ways that it does that, and one that it really famously did that on was, for example, with the WannaCry, is it will call out to a really obscure URL, like 3F49728BBCD, .com, knowing that that domain doesn't exist. But quite often in malware analysis environments, you allow any connection out because you want to see what connections that the malware is trying to make. So for any connection, you'll return an HTTP 200 response. In WannaCry's example, it knew that if it got a response for a non-existent domain, it must be getting examined, and therefore it turned itself off. So what this one here does, this DGA app, is it looks for in your web logs, your proxy logs, domains that don't look like normal domains. And so what they've done here is they've said, okay, if you look on point 1, where it says the two classes are legitimate and DGA, so domain generation algorithm, and it's got the predicted class and the actual class, and for each of the different types of algorithms we've looked at and said, well, what are the sort of how accurate are each of them? So we've got random forest classifier, we've got support vector machine decision tree classifier, and logistic regression, and we can see that actually looking down at the bottom, picking the right algorithm is actually really important in this case, because if we'd gone with straight up logistic regression, we would have potentially that's nearly 3,350 false positives. Whereas with a random forest classifier, we've got a far better rate of prediction. I mean, there are still some false positives, but we get a far better result by picking the correct algorithm. So in all cases, it really is about understanding the question that you want answered, and about understanding which algorithm is probably best suited to answer that. So yeah, selecting the optimal algorithm is important. Using noisy data, so again, go back to that red tie example. If you put data in there that's not relevant to the question you want answered, you're likely to have a harder time of getting the correct answer out of that machine learning process. I've mentioned earlier numerical field values, so not all algorithms are affected by that. The weighting of purely a number and its importance. Generally, you can get around that by, if you do have to have a number there, you can just put a letter, an underscore, and then the number, which you can do with eval. So and then not understanding what MLTK has to do with data. So this is a bit more in depth than I want to go into today, but I want to just touch on it. So when you provide data to the machine learning toolkit, it has to look at that data, and it looks at how many, for example, events that you pass in have a null value in a given field, and then it might drop off some of that, depending on which algorithm, and it mostly applies to the application of something called one-hot encoding. It will reshape behind the scenes your data. So you might think that you're not giving it a great deal of data, but actually in order to make it work correctly with the machine learning algorithm through Python for scientific computing, it has to rearrange your data into a way that the algorithm understands better. And as you can see at the bottom of that example there, we've got 3 by 4 is what you might have given it, but that then turns into 4 by 4 if you want to do what's called one-hot encoding. And one-hot encoding is effectively, if you see on the example there, the first one is an apple, so it gets a 1 for an apple. It's not a chicken, so it gets 0, and it's not broccoli, so it gets 0. And it's basically just being able to standardize so that each item has all of the classification fields, and so that the algorithm can say, this is definitely this, and it's not this. Therefore, I can treat it purely as an apple, or a bit of chicken, or some broccoli. So it's about standardizing, but what that can do, like I say, is it can mean that the algorithm at the back end is given more data than you think you are giving it, which means that your memory requirements might be higher or your CPU load might be higher. What Splunk have done in order to prevent this sort of killing your search head is in MLSPL.conf, which is mentioned there. They've put some limitations in place so that for most setups, what will happen is you'll get an error rather than a crash on the search head. And what you can then do is go in and say, well, actually, yeah, I want to tune that setting because I know that I've got sufficient RAM and I'm not going to cause problems for my instance. And I'll just show you a quick example. So on here, this is the DGA thing we were looking at a minute ago. And you see here that for the support vector machine, I've got a warning here. So it has completed, but I've got a warning. And it's basically saying here, as I mentioned a minute ago, actually, you've given me more events than my default settings allow. I'm only going to look at the first 10,000. And if you want me to change that behavior, you have to go and change the entry in MLSPL.conf. Useful resources. So we've had a little bit of a look at the machine learning toolkit. And to be honest, I think we've talked more about machine learning as a concept and how the algorithms work. Some things that I would recommend if you want to start dipping your toe into this. The docs are extensive and very useful. And actually, if you go into Machine Learning Toolkit, if I switch back up here, in the actual menu bar at the top there, you see that there's a link to the docs. There's a link to some video tutorials. And I think they actually take you here. So Splunk themselves have got nearly 50 videos now, all the various things, how little tools work, how algorithms work, how to select algorithms, lots and lots of good stuff there. Other stuff, so .conf talks. So every year after .conf, Splunk will upload all the presentations, you have slides, you have videos. There's loads of good stuff there, and you can select your actual level of confidence. So you can go from I'm a beginner to actually I'm quite confident and I want to know the details and the meat on the bones. So lots of good stuff there. This chap here that uses the username CentDex. If you go onto YouTube and put CentDex in, you will find literally hundreds of really useful, really detailed and explanatory videos on machine learning in general, machine learning using Python, using various different frameworks like TensorFlow, scikit-learn, and so on and so forth. Speaking of scikit-learn, scikit-learn and pandas are, as I said earlier, they are sort of the engine that's brought into Splunk using Machine Learning Toolkit. Their documentation is also very good. The picture there is a book that I highly recommend as well. I believe the owners actually now made this free. I bought it a year or two ago, but I think they've actually now made it free and it's on GitHub. You can go and have a look at that. And then finally, this one here, this course at the bottom, fast.ai. It's a really interesting approach to learning how machine learning works and deep learning and so on. And effectively, the traditional way to learn it is to go away, learn the theory, learn how this algorithm works, how that algorithm works, learn this statistical technique and so on. And by the time you get to even doing anything, you're bored with it. It's all very dry. With fast.ai, they flip it on its head and they say, here, look at this. Isn't this cool? This is how it works. You've just done some machine learning. And you're literally, within an hour or two, you are building models. You are doing classification and you're producing results. And then they sort of take it back and say, well, how does it work then? And you work backwards. So the example they gave is, a child learning to play a game of rounders doesn't first have to learn, fluid dynamics to understand the path of a ball through the air or Newtonian mechanics. They don't learn any of that. They just pick up the bat and play. So highly recommended that course there. And like I said, all of these resources here are useful to get your grip on what machine learning is and how to approach it, because I think it's very important that although it's very, very easy to install the machine learning toolkit, it's the understanding of the process behind it and how different algorithms work and how they interact and what sort of data is useful for one or the other. So getting a real sort of general understanding of machine learning concepts is probably important before you start sort of heading off into the world of machine learning and Splunk.